This video will cover the addition of organometallic reagents to carboxylic acids and their derivatives. Remember that the structure of a carboxylic acid looks like this. And the two carboxylic acid derivatives we will discuss are acid chlorides and esters. Notice that all of these contain a carbonyl and are therefore electrophilic. First, let's consider what happens if we add an organometallic reagent to a carboxylic acid. For example, if we add a Grignard to a carboxylic acid in the presence of ether followed by the addition of water, what product do we get? Take a moment, pause the video, and see if you can predict the products that we get from this reaction. Because the carboxylic acid is protic and the Grignard reagent is a strong base, what we get is the deprotonated carboxylic acid and the protonated Grignard reagent. Typically, this is not a particularly useful reaction. However, the carboxylic acid derivatives are not protic and therefore they react differently. Next, let's look at what happens when we add an organometallic reagent to an acid chloride. Acid derivatives require two equivalents of the organometallic reagent to react completely. If we react this organolithium reagent with this acid chloride in hexanes followed by the addition of water, we will get a tertiary alcohol as a product. Now let's look at the mechanism for this reaction in order to understand why we get this product. In the first step of the mechanism, the first equivalent of the organolithium reagent attacks the carbonyl carbon of the acid chloride, giving us the tetrahedral intermediate. The tetrahedral intermediate then collapses to give us a ketone, kicking off chloride as a leaving group. The ketone then, remember ketones also react with organometallic reagents, reacts with the second equivalent of the organolithium reagent. This produces a second tetrahedral intermediate. This tetrahedral intermediate cannot collapse as there is no leaving group to reform the carbonyl. Therefore, this is where the reaction stops until the addition of water. Addition of water protonates the alkoxide ion, giving us the final product, a tertiary alcohol. Next, let's consider the addition of an organometallic reagent to an ester. Just like we saw with an acid chloride, an ester requires two equivalents of the organometallic reagent to react completely. If we react this Grignard reagent with this ester in the presence of ether followed by addition of water, we again get a tertiary alcohol as the product. Pause the video now and see if you can write out the mechanism for this transformation. It is analogous to the transformation of the acid chloride. In the first step, the first equivalent of the Grignard reagent reacts with the carbonyl of the ester, forming the tetrahedral intermediate. The tetrahedral intermediate then collapses to kick off the leaving group of the alkoxide ion. This produces the ketone, which can then react with the second equivalent of Grignard reagent to form a second tetrahedral intermediate. Just like before, this is where the reaction stops because there is no leaving group to allow reformation of the carbonyl until we add water to protonate the alkoxide ion, again to give us our tertiary alcohol as a product.